Hello everyone, welcome back to Calculus BC. We're in lesson number 31 where we're going to talk about arc length. What we really want to do is we want to use an approximation, an idea of an approximation of a curve to figure out how long something actually is. And so the approximation part comes in the fact that we're going to create ourselves a line segment that connects 2 points to our curve. And what we're going to end up doing is finding the distance of this curve. And then the more of these curves that we add, then the better we're going to get to the approximation of our actual curve. The arc length formula is actually derived from the distance formula. So you guys can clearly see the distance formula right here, and we're going to start manipulating this to the point that we're going to get the actual formula for arc length that you're going to use in calculus. So the first thing we're going to do is we're going to take the distance formula, and we're going to change x of 2 minus x of 1 as simply a delta x, right? That's what that is. We're changing x of 2 minus x of 1, well, that's how much our x is changing. And we're going to go ahead and put a little I right here. And so we're going to keep squaring that. And we're going to do the same thing with the y. We're going to do y sub 2 minus y sub 1, and that's just going to be a delta y. Again, a little I. And you'll see what the I comes in a second. It's really just delta x quantity squared plus delta y quantity squared. And so what we want to do now is we want to do a sum of these things. So we want to keep adding, as I said before, we want to add more and more and more of these segments to the point that they're actually going to create this curve, right? As I keep going line, 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 it's going to kind of fill in this actual curve. So what we're going to end up doing is we're going to take a segment notation, and we're going to have an n amount of lines, and we're going to start where I is going to be equal to 1. And then again, that's why we have our y. So our first delta x, our first delta y, and then we're going to keep going more with that of our formula. So we're going to go ahead and just rewrite our formula down. So this gives us a way to create all these segments to the point where it's going to start filling in to actually the point where we're going to get the distance of this arc. Now, again, we're not going to use this, so don't worry. This is not the formula that we're going to use to actually calculate the arc length. It's actually much simpler than that. But what I want to do is I'm going to go ahead and rewrite our function down here. So again, our segment notation, and it's again the number of times we're going to do it, how many times we're going to have, how many numbers in our sequence. We're going to go ahead and start again, I equals 1. And I'm going to go ahead and pull out, and this is going to be weird, but I'm going to go ahead, key square root. I want to pull out a delta x. I'm going to pull out delta x in our function. So if I pull out delta x, actually I'm going to pull out delta x squared in our function. So if I do that, then this is just going to simply be 1, right? There's only one of them here. So 1 times delta x is going to be delta x. And then here, I'm actually going to do delta y I all over delta x I quantity squared. So the reason I was able to manipulate that is if I were to actually distribute the delta x back in, then I would get this back. So I actually haven't changed my function at all. I actually haven't changed it. And so now what I can do is I can, remember, now these are two things being multiplied together. So just like in Algebra 1, if I ask you guys to multiply, take the square root of x squared times 3, you guys know that you can take the absolute value of x times the square root of 3, right? You can pull the square root of x squared out, right? You can pull the x out of this. Well, I can do the same thing with this. This is a product here, so I can leave. So let's go ahead and keep our segment notation for one more time. And so what's underneath the radical is going to be 1 plus dyi over dxi quantity squared. And then I can multiply that by delta xi. And that's just simplifying the square root of this quantity squared because they cancel each other out. Okay, so now what I can do, and the reason I'm going to keep this positive is because our delta x is going to be positive when we actually look at arc length for this. And so we can learn, and we have learned, that segment notation can be rewritten actually as an integral from a to b, and we're going to keep our function, so 1 plus, and then we're going to just simplify this as dy over dx, quantity squared, and then we're going to have this as our delta x. So this is going to be the formula that we're going to use when we actually solve arc length. So this was probably a little complicated, but the process is really simple. So what we really have to do to find the arc length is the a and the b, by the way, are going to be, the interval that we're looking for. And then we just got to find the derivative, square it, add 1, take the square root, and there we go, and integrate it that way. So let's actually look at the 3 quick examples that we have for this. And so here's the formal definition for it that you guys can pause and read, but I have just showed you what this is. So it's our first derivative, which again is a change in y with a change in x. So f prime of x. We're going to square that, we're going to add 1, take the square root, and we're going to integrate from a to b. So example number 1 says find the length of the curve, which is an arc length, of our function y equals x to the 3/2 power, from the point 1, 1 to the point 4, 8. Now this question is actually a little misleading only from the fact that we only care about the change in x. So when we find the arc length of this, we're going to actually just look at the distance from x1 to x4. So we don't really care what the y values are, we just really care about the x values. So example number 2, we're literally going to integrate from 1/2 to 2. And so when we're finding the arc length, we're going to go ahead and do the square root. And these, again, are always calculator problems, by the way. We're going to do 1 plus, and then all we have to do is find the derivative of our function. So this is going to be 3/2 x to the 1 less power. And so we're going to take the derivative, we're going to plug it in here, and we're going to square it. And then we're going to do dx. And that's all we're going to do. We're going to plug it into our graphing calculator. And so if we actually were to measure, so if we started on this curve at 1, 1, and we trace the curve to the point 4, 8, we would go a distance of 7.6337. That's all you do for arc length. So if I ask you guys to find the arc length of this function, well, you're going to integrate from 1/2 to 2. You're going to write the square root of. You're going to get 1 plus. All we need to do now is find the derivative. So the derivative of this is going to be 3/6 x squared. And then this is going to be, well, this is really going to be 1/2 x to the -1, right? That's what this is. So it's easy to find this derivative if you just think about it like this. So it's going to be minus 1/2 x to the -2 power. So if I just want to really quickly simplify this, I can have this is going to be 1/2 x squared, and this is going to be minus 1/2x squared. So once we find that derivative, we plug it directly into our function. So 1/2 x squared minus 1/2x squared. We're going to square it, and then dx. So don't forget that when you are doing these problems that you still have to find the derivative, and you have to square it. And then if we plug this into our graphing calculator, we're going to get 2.0625. And so this is the distance of this curve from x equals 1/2 to x equals 2. Cannot make it more challenging than this. Find the arc length given by the function x is equal to 1 plus y to 3/2 power on the interval from 0 to 4. Well, up here in our definition of our definition of arc length, well, then we're going to use this one. It's the same problem. Our C and D is going to represent where our y value is, and then it's going to be another derivative now with respect to y, because all of this is respect to y. So when we do this problem down here, ladies and gentlemen, we're going to go integration. We're going to integrate from 0 to 4. We're going to take the square root of 1 plus, and then we're going to take the derivative of this. Well, the derivative of this, and we're going to do it with respect to y now. So we're finding dx over dy. So we're going to have x is going to be 0, and then we're going to have 3/2 y to the 1 less power. And so this function right here, we're going to simply take it, rewrite it where our derivative should be, or where it is. We're going to square it, and we're going to do dy, right? No dx, we're going to do y there. And we're going to plug it into our graphing calculator, and we're going to 9.073. That, ladies and gentlemen, is the short way of me telling you to find arc length. You do an integration from a to b. It's always going to be, now this is for Cartesian rectangular coordinates. We will do other ones. We'll find arc length later on for polars, but right now for this is all we're going to be doing. It's going to always be the square root of 1 plus the derivative of the function, quantity squared, under the square root, dx or dy. So I hope that's helpful, and I'll see you in the next video.